Shravan will take us to the interior of our own star, Sun. And it is exciting because he works on Sun, helioseismology, and again, another person with machine learning, right? So let us eagerly wait what is there inside our Sun. So please.
Thank you for inviting me, Manjari. I was just telling her that I really am enjoying this session with these long talks, and the talks have been so far very good. So, I mean, of course, I'm not complimenting myself, but I'm just saying that I enjoyed the morning quite a bit. Okay, so I sort of wanted to have two halves to my talk, with a little bit about machine learning, since we've heard quite a bit about it today, and then I'll go to my bread and butter, which is seismology. So many of you may have heard or not, I don't know, about what space weather means. Space weather is the impact of the sun on our surroundings. And so there's a lot of things that machine learning can do to help us understand the physics of this. So let me show you some spectacular footage. Here's a continuum intensity image of the sun by the helioseismic and magnetic imager. And you see this magnetic flux. So the black stuff is magnetic flux that's sort of emerging at the surface. And yeah, so here it is. It seems to be growing bigger, and there's some little stuff coming here. But interestingly, this stuff, there was another thing. Yeah, this stuff vanished, and this huge thing showed up later. And so that's a very remarkable and interesting physics as to what constitutes, when sunspots, these basically become sunspots. So we have right now 0 prediction time as to when sunspots appear. And these sunspots basically create large magnetic fields, which in turn create solar flares and have a significant impact on our space weather on Earth, on telecommunication, and so on. So there's a lot of really interesting physics here. It's driven by what is known as magnetoconvection. So there's magnetism, and there's turbulence, and there's very complicated fluid dynamics. So you have these complex emergent phenomena which are driven by processes in the interior that we don't know. We don't know where the seat of the solar dynamo, as it's called, is. So these, of course, have an impact on the surface. You see all these magnetic, the red is field that's coming to you, magnetic field that's coming to you. Blue is the magnetic field going in. So you see these bipolar, so you see the red and blue, for instance. You see these bipolar collections of magnetic regions. And if you go higher up, typically about 40,000 kilometers, if you will. And so you go higher up into the solar corona, and you're seeing hotter and hotter plasma, and you see the impact of this, so the magnetic lines that are sort of traversing into the corona. And these can reconnect and create large, high intensity, high energy, events, violent events that impact, as I said, the interplanetary medium significantly. So here's a spectacular image of a flare, so you see this. So what's happening here is, we're seeing it in a certain electromagnetic band pass. So stuff comes in and out. So you're not witnessing the entirety of the physics, but what you're witnessing is stuff that's happening within a certain temperature range. So these are field lines. These are known as coronal loops. So you see this, and then they dynamically reconfigure because they're driven, as I said, by these intricate fluid motions at the surface that are twisting the magnetic fields more and more intricately, and they become increasingly unstable. Then they reconnect, and during this process of reconnection is typically a very dynamical and violent phenomenon. So then this stuff gets strewn out of the sun. This stuff comes to us within minutes, basically. The electromagnetic radiation comes to us very fast. The high energy particles take about a day. And so there's a very rapid, can very significantly and rapidly affect us. So anyway, so you have a variety of phenomena. You have solar flares, essentially 0 warning. Coronal mass ejections take a little more time because they're huge clouds of particles. So they take about 20 hours to anywhere up to 4 days. And they can, so yes, these high-energy particles take longer, but they can also much more significantly impact us because they affect the geomagnetic, they have a significant impact on Earth's magnetic field, and they can penetrate into the Earth and then knock out huge power systems and so on. So these have significant impacts on us. I don't need to go into this. And so you can see all these dramatic things, but they're actually not dramatic, they're actually true. So this could have pulled the plug, as it says. It's a very interesting thing. In 2011, I believe, this is 2012, yes. So 2012, there were 3 coronal mass ejections that happened one after the other. And so each one sort of clears out the path for the subsequent coronal mass ejection. And so the solar wind, sort of the path on the solar wind to the Earth becomes clean. And so by the time the third one comes around, basically it's devastating because the full intensity of this cloud could come and hit us. Thankfully, the Earth is a very tiny fraction of the solid angle of the sun, so it missed us. But if it did hit us, Lloyd's of London says that we would have lost $2 trillion, or the damage would have been about $2 trillion because of our contemporary dependence on telecommunication, electronic machinery, and so on. So it can have a really significant and profound impact on us. And some of this stuff, if it does impact us, is not something that you recover from, in 5 days or something. It takes decades to rebuild the infrastructure that this could. It's a bit like an earthquake that splits the Earth apart or something. I mean, obviously it's more dramatic. I mean, it's not going to split the Earth apart, but it can have really significant consequences on our supply chain and our way of living, contemporary way of living. Okay, so anyway, so there's some things that show how significant these can be. I don't need to get into this. But what I want to say is that there's a very large number of instruments that are monitoring the sun and the magnetosphere of the Earth. Here's the Earth, here's its dipole moment, swept away by the solar wind. So you can see this thing is open field lines that reconnect much farther down. And so here's the shock. Solar wind shock. And so anyway, so magnetopause as it's called. And so the solar wind is coming towards us. And all of these are taking a variety of different measurements, some of the sun, some of the solar wind, and so on. So there's a tremendous opportunity to use machine learning because there's a lot of information that human beings can't easily look at. So as I said, there's a huge amount of data. We can train machines. There are many holy grail problems. There are many engineering problems, such as, as we become a spacefaring economy and spacefaring society, you have to know when the sun is going to create, these dramatic events. And so if you can predict it, then you can prepare for it. And so, it will become an important engineering problem as well. But I'm not interested in the engineering problem. I'm going to describe a physics problem that you can do with machine learning. So the question is, can we say something about when solar flares are going to happen, or what are the physics that lead up to a solar flare? So a solar flare is a very complicated, highly nonlinear magnetohydrodynamic phenomenon that happens, as I said, it's a magnetic reconnection. So it happens in very short time scales. It's a huge range of spatial and temporal scales. So it affects field lines that are thousands and thousands, tens of thousands of kilometers long. But the initiation could itself have the rupture, the reconnection could happen on microns to millimeters. So there's a huge scale range temporally and spatially. So it's a very non-trivial thing to model. So typically numerical simulations cannot get into this parameter regime. So data are perhaps the best way that you could really understand this. But a lot of things are happening during a solar flare. There's lots of motions of different things. There's plasma is moving, magnetic fields evolving. So there's a lot of dynamics going on. And as a human being, you can only monitor so many. Contemporary mathematical methods can only take into account a finite number of parameters. This is a very high-dimensional system because lots of things are happening, both spatially and temporally. And so when you have access to these data, to such high-quality data, the best thing you can do is basically apply machine learning, because this is a device with which you can sort of assimilate the entire data set. So typically, flares are split into these categories. A, B, C are really quite dull. They're not of particular interest. They're very low magnitude in terms of X-ray flux. But M and X can affect us. The X is particularly significant. X can knock out power systems on Earth, and so are of great interest to us. And so the frequency described by power law statistics. So the most frequent ones are the ones that are weakest in amplitude or weakest in magnitude and so on and so forth. So there's a power law that goes down from A to X. The A is constantly happening, but X is very infrequent in a power law sense. So, but we don't know what these precursors are. We don't know what's going on. So what the helioseismic and magnetic imager, which is an instrument on board the Solar Dynamics Observatory, NASA instrument, flagship heliophysics mission from 2010, does is it monitors the sun and constantly looks at active regions. There's a thing that basically this algorithm is not a machine learning. This is not a machine learning algorithm, but essentially identifies these active regions or magnetic regions, and then it says, okay, here, and from these sort of images, it cutouts, as it were. You get a number of parameters. Each of these cutouts, this is the simplest way to analyze this. You can do much more complicated things, and I'll describe that very briefly towards the end. But the simplest thing you can do is from each of these cutouts, from this automated algorithm, you can get a number of simple parameters, such as the average unsigned magnetic flux, average current, average something. So there's some 40 parameters that you can derive. It's just spatial averages over that entire cutout. So this active region, for instance, is associated with these. I've only listed a few of these, but these are simple spatial averages over this region. And one question that we ask is, how do these features evolve before and after? And you might think, well, this is a really trivial question because there's a finite number of parameters. There are only like 25 parameters. But even this, interestingly, people had not been able to fully appreciate before before we did this with machine learning. So I'll describe some startling insights. Thankfully, Ajit has already described what SVMs are, support vector machines are. There's essentially a machine learning framework to draw a hyperplane or a complicated, geometrically complicated, at least in some axis. It straightens out, it does a number of nonlinear transformations, and it separates out what we might say is a flaring class and a non-flaring class. So the goal is, if I give you these parameters, the ones from the previous slide, can you tell me if it's flaring or non-flaring? That's the simple question, the binary answer, is it 0 or 1? And what it does, as I said, is that it takes this high-dimensional problem and straightens it out in a series of nonlinear transformations, and it says, well, this is the flaring class and this is the non-flaring class. Not quite as cleanly as this, but remarkably cleanly, much better than human beings would be able to do, for instance. So, and also I would like to note that typically in all problems, in a lot of problems in astronomy and astrophysics, in the world, in real world problems, they're class imbalanced problems. So we have an overwhelming preponderance of things that don't flare. So if my algorithm kept saying it's not going to flare, it's not going to flare, it would be correct 95% of the time. So if you just use plain accuracy as a means of saying my algorithm is correct or not, then you don't even have to devise an algorithm, just say no, and you'd be correct most of the time. So the challenge is in that small 5% and getting that small 5% right. So here, for instance, so the machine works, and machine works really well, actually, with what is known as a true skill statistic. It's 80%, which is a very large number. True skill statistic of 0 means you flip a coin. So you just say, if the coin says heads, then you say it's flaring versus non-flaring. But a true skill statistic of 80% says it's 80% beyond that. So we really have extracted a very substantial amount of information from this. And this is the question: what is the machine seeing that humans do not? And this is the goal of this. I don't care to put out an algorithm that is going to tell you whether there's going to be a flare or not. Someone's going to do it for sure. Someone, in fact, has already done it to some extent. What I want to know is interpret what the machine has learned. What high-dimensional correlations has the system gathered? So here you can see this machine. This is a video, what is known as a magnetogram. So we're seeing the line-of-sight magnetic field. And this is a time history. At each time instant, I'm feeding in the machine those 25 parameters that I described to you. So basically, it's saying the machine is saying no, 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 and then suddenly it flips into saying yes, yes. The red is yes, it's flaring. Sometimes it makes a few mistakes, but it's statistically significantly yes for a period of time here. And then these black lines indicate when the flare actually occurs. And so you can trace it to, if you look here, as to what's happening, you can see that, okay, it's fine. It's saying there's nothing particularly interesting happening. Some black stuff appears, which is the field that's going inside the sun, so it sort of flips into a yes. And then now you can see something is emerging and evolving here. So now it suddenly starts to note. So I've discovered by this process a feature, a state. The machine is changed, the active region has changed states. It's a state transition, if you will. Not really a transition, because that's a bit more, that word, the term has connotations that I want to avoid. But essentially, there's some interesting physics here. And so very briefly, I don't want to go into too much because I want to get into my seismology. But so what the machine finds is that for days prior to this, it lies in a flare productive. So the magnetic field is ready to flare. It's been ready to flare for days, which is a very remarkable thing. So no one knew this. So the way I would see this is the machine is saying for days, this is when, 0 is when the flare happens. So time equal to 0. It's saying for a long time before, the machine is saying with high probability that it will flare. And this is the nominal. If it's non-flaring, it knows, anyway, don't worry about the blue. So anyway, it means with very high accuracy, I know that it's going to flare for a long time before. And even after this, it persists in the state. So that's one interesting thing. And then we also see this very remarkable thing. Again, all of these features were not known before. I want to emphasize that all I did was to take simple parameters, the 20 parameters of this system, a time instance. Of course, we're observing the sun continuously. Just from this simple analysis, people have analyzed this before, and they have not discovered these truths, or not truths, whatever, these correlations. But there are remarkably interesting physical insights to be extracted using machine learning. So you see here, for instance, the current rises sharply prior to the flare. This is a statistical thing. It's not an individual thing, but over an ensemble of flaring regions, you see this. It rises and then sharply falls. So there's sort of a buildup of net current helicity, which is essentially electric current, and then a release subsequently. Again, not known before, so that's very, very interesting.
This was trained on just previous data?
Yeah, all trained on prior data, yeah. So we have 7 years of data, for instance. So I don't want to really get into anything else. There's also magnetic field emergence that we're working on, so I don't want to, I won't describe that now. I will go to my bread and butter. It's a complete topic change, sorry. So this is what I do most of the time, which is helioseismology. And a particular problem that I've been focused on for some time is to appreciate the structure of solar convection. So the sun is, you would argue, is extremely, and justifiably so, is a very well-studied and presumably well-understood object. But what we've realized in recent years is actually we've realized, I think we've always known it, but I think we've realized it more sharply in the last few years that we actually don't understand it very well at all. And for the simple reason that the dominant physics that drives the majestic solar behavior occurs in a parameter regime that we are unable to access through laboratory experiment or computation on Earth. So one fundamental aspect of it is solar convection. The outer third by radius of the sun is in a state of convection. So the movement of material movement transports heat, basically. And the structure of this convection decides what happens in the sun and what happens outside the sun. So in a sense, convection is at the heart of many fundamental physical phenomena. The most challenging and least understood, one of the least understood things about the sun is its differential rotation. So that is to say that the equator rotates faster than the pole. It's a fluid, so it's not solid body rotation necessarily, but remarkably, it rotates faster than the pole, and in a way that sort of has surprised theorists, and no one has really been able to explain it despite 3 decades of us knowing this. So this differential rotation is an outstanding challenge in solar physics. We know, or we think rather, the differential rotation, there's another circulation that's sort of secondary, not the most important, but this is sort of a critical thing. We know that combined, these two large-scale circulations, or movements of fluid, sustain the solar dynamo, which is large-scale magnetism. So it generates and sustains this large-scale cyclic magnetism. So all of you know that the sun is like a bar magnet and keeps flipping every 11 years. And somehow these two circulations in tandem are able to support this. We don't exactly know what the seat of the dynamo is. We don't know what the physics is, and which in my previous brief presentation described how that impacts us in a variety of ways. But even otherwise, the physics of convection is very, very interesting and remains to be explored and not understood. So thermal transport in itself remains an outstanding challenge, and there are these long-range correlations which drive these phenomena in the sun, including magnetism. We don't understand what these long-range correlations are. So in some ways, it's not a fundamental problem in the sense that we don't, we sort of understand what the sun is made of, but how the sun works is something that is not well understood. And so these parameters, which are sort of irrelevant, I don't really want to get into it, but I want to point out that these are very large numbers or very small numbers. So it operates in an extreme regime that no fluid on Earth can be pushed to. So what we try to do is we try to measure the spectrum of convection. What is the amplitude, power spectrum, if you will? What is the amplitude of convective motions as a function of spatial scale? And so on the horizontal axis here, it's spherical harmonic degree, like wave number on a sphere. And here's the energy in these units, kilometer cubed per second cubed. And so what we discovered some years ago is that this is numerical simulation, this light blue curve. Ignore these other curves for now. But these light blue calculations are three-dimensional, very, very expensive, very large calculations of convection in a three-sphere. And they show convective power to be here. Seismology, which is what I do, I'll briefly describe what I do in a minute, constrains it to be nearly 3 orders in magnitude smaller. So that's a problem. Certainly for an object as well understood as the sun, the fact that it's so far apart means that we don't actually understand the sun at all in a very fundamental way. So this is sort of the focus of my work, ever since this paper. And we want to try to measure the spatio-temporal correlation in more sophisticated and using better techniques. Another major challenge in the sun is in typical turbulent flows, the largest spatial scales contain all of the velocity power. So if you're interested in turbulence, you know that this is sort of the spectrum of turbulence. The large scales are where all the power lies. But the convective power spectrum that you directly measure right at the surface shows that the power declines steadily. Now, for non-fluid dynamicists, this is a detail, but for fluid dynamics people, this is a big problem. Like, we don't understand what's going on here, why the power reduces. Sorry, horizontal axis is harmonic degree and vertical axis is velocity. So it's decreasing as a function of harmonic degree or decreasing as a function of increasing scale. So this is a big challenge. So we don't really understand some of the basic physics of the sun. And as I said, this is an outstanding challenge in solar physics. And in fact, other stars, we recently had a paper where we showed that a variety of other stars, using what is known as astroseismology, the seismology of stars, we're able to show that it's not just the sun, but other stars also have this differential rotation. And what's remarkable here, so first let me explain. This is a cutout of the sun. And you see here that this is nanohertz. This is the rotation rate. The equator is rotating faster than the pole. All of conventional atmospheric physics and all the literature prior would suggest that the rotation contours look like this. It's like they take these cylindrical shapes, like these iso-rotation contours would be cylindrically shaped like this. But the sun does something very different. It's some funny angle. And sorry? Yeah, it's one axis. You can think of it as the z-axis or whatever. This is the rotation axis. We're approximately perpendicular, rotating in the solar system perpendicular, a few degrees off, but approximately you could think of it as the sun is rotating like this. So this is a major challenge. How this has moved away from being perpendicular into this funny angle is not at all understood, like really not understood. Numerical calculations can't even predict this. I mean, there's no trivial way there's no robust way, if you will, to get rotation contours like this. So it's one of these really basic things that we don't understand. And helioseismology is sort of the only way that you can really attempt to probe this.
So is there a complete symmetry between the equator to 0 and equator to pi?
You mean north-south symmetry? That's a good question. I would say broadly, yes. There are some technical things that I can discuss with you after the talk, because there are sunspots that ruin the symmetry, and there's a variety of more complicated things happening. Broadly, yes. Broadly, yes. Actually, it's an interesting point, though. I should think about that a little bit. It's a good point. So what you see here are oscillations of the sun. So these are known as solar oscillations. They're 5-minute oscillations. That's the dominant period. So you have turbulent convection at the surface. That's like raindrops. So they overturn, and then you have this fluid that goes inside the sun, and you can think of it as a rain that's falling all over the sun all the time and exciting these. So it looks like a TV static, if you will, like you're seeing television. And so these produce resonances. These waves, they're excited. They go within the earth, within the sun, and they come back up to the surface, and they form these resonant cavities. And so the idea is that you combine different modes, different resonant modes of the sun, and you can image different parts. For instance, there are modes that are the breathing modes of the sun. The entire sun is oscillating, for instance. That mode goes all the way to the core. But other modes, they traverse the surface layers. So you can combine, mix and match different modes, and then try to image different parts of the sun as a function of 3D and time. So it's like 4D imaging of the sun. That's sort of what we do. And the dominant observational technique is surface Doppler. So we have a Doppler, like a space. This is all space-based. MDI is a space-based instrument, and it's observing, I think, iron 1, I believe, or it's not iron, nickel line Doppler shifts, and then you're able to generate these line-of-sight projected velocities. So what we see is this. This is the dominant observational quantity. This so line-of-sight velocity field as a function of time. We only observe the visible half of the sun. We don't obviously observe the distant side of the sun. So what I do is something known as normal mode coupling. So normal mode coupling is a type of helioseismology. It has a very illustrious past. It was first, I think, introduced in quantum mechanics, and then subsequently went to terrestrial seismology. So they've had a number of very fundamental advances in appreciating how, for instance, differentiation of the Earth and so on. So many fundamental questions about terrestrial structure were answered using normal mode coupling, and now we're using it for the sun as well. And so the basic idea relies, as I said, on quantum mechanics, and the first Born approximation is a single scattering approximation. The idea is that, let's say I have a conception of what the sun is, and that's the reference model. My reference model is very simple. It just tells me what the density is as a function of radius, sound speed is as a function of radius, and so on. So quantities is a function of radius. But it's non-rotating, it does not have convection, it's axisymmetric, which is to say that it does not have any variations as a function of theta or phi, and it is non-magnetic. But the true sun, or the sun rather, has all of these features and is decidedly not axisymmetric. It has sunspots, it has all sorts of really complicated things, it has convective features that are non-axisymmetric. So, and is time varying. This is non-time, it is temporally stationary, and this is time varying. And so the idea is, okay, now my conception is clearly not the sun, but the hope is that it fits within the realm of perturbation theory, which is to say that the reference model is reasonably good, but with sans, some modulo, some corrections. So I need to make those corrections. I need to perturb the reference model to try to match it to the sun. And normal modes, or the modes of oscillation, are a way to achieve this. So the idea is as follows. This reference model. So first of all, I would say linear theory for waves, the small amplitude theory works extremely well. We know this. So because it's linear, there are a complete set of eigenfunctions. This orthonormal and complete. And so the same, of course, for the sun as well. But what happens is, because these eigenfunctions form a complete basis, every eigenfunction of the sun can be expressed as a linear combination of the eigenfunctions of my reference model. So this particular this ability to write this eigenfunction like this is to say that the solar eigenfunction is coupled with respect to the reference eigenfunction, which is to say that these eigenfunctions can be put together to build a solar eigenfunction. Turns out that I can measure this alpha k prime k, which is the coupling coefficient. So if anyone's done quantum mechanics, as you know, these are the scattering coefficients, so they're sort of ubiquitous in fundamental quantum mechanics literature. So I go off and I can measure millions of these things between different modes k and k prime. That's what I do. I measure millions and millions of correlations from all these mode measurements. And so it turns out that this alpha k prime k is directly proportional to the sum. You don't need to read all these mathematics, but it's very tedious. There's a lot of algebra that goes into it. But you can relate these to that phi omega Lm was the quantity that I measured. I was describing to you line of sight projected velocity field. and I can measure it using this correlation function. So what we do is we use the entire 22 years of data that we typically have for the sun, and so anyway, so you can do this entire analysis. I won't really go into the details, but there's a very beautiful mathematical theory that follows. You use something known as the Chandrasekhar-Kendall decomposition. It was by Subramaniam Chandrasekhar, who said any vector on the three-sphere, or two-sphere rather, can be broken into what is known as a poloidal term and a toroidal term. And so you can sort of directly decompose this flow field, and you can express each of these quantities, U, V, and W, as these measurements that I was making. So we write what is known as an inverse problem. I make some measurements of the surface of the sun, and I connect it to the properties of the flow underneath. Now, there's a couple of things that we as a group in India are doing for the first time. So this method has not been well explored for the reasons that it's very abstract, it's mathematically heavy. It's very little data massaging, but there's a great deal of mathematical rigor that's required to interpret these measurements. So there's not a whole lot of people that are doing this in the world. So our group in TIFR is basically sort of leading the charge. And the first thing when you introduce a new measurement technique, it's not just a new mathematical technique to do something, but it's a new measurement method, is to test that it works and show that you benchmark it against something that's known. And so we've already sort of made a first step towards it. I don't really need to explain what this is. Sorry, did you have a question? No. So this is we know that there are Rossby waves on the sun. Rossby waves exist on the Earth as well. They cause all these atmospheric phenomena, polar drift and so on. And so we observe Rossby waves in the sun using this method and benchmark it against these guys who've independently observed it. So this, to me, is a very, very important first step, is benchmarking a new method against prior existing discoveries. So I don't want to describe this, as I said, what this means, but that was a very important first step. As I said, the benefits of doing what we're doing is, first of all, there's no one else doing it. So we have a new insight into the sun, and we want to try to maximize our achievements before other people start to follow up. And as I said, it's been recently validated against these Rossby wave detections. And you can measure the spatio-temporal variations of flows, for instance. It's the first method to do this self-consistently, so we're sort of happy about this. And there's a number of other reasons, and it can be expanded to discover other things in the sun, like G modes and so on, which I won't really get into in detail. So I just want to very briefly say 2 or 3 things. I don't think this is the most fluid mechanically inclined audience, so I won't bore you with all these fluid mechanics ideas, but I just want to say what the measurements are in the end. So the first thing that we see is this is a numerical simulation, and these are observational constraints. And it continues to be a significant problem in that the numerical calculations appear to be significantly larger, not quite by 3 orders in magnitude, but they're still quite a bit larger than our observational constraints. So that the problem that I described earlier, that the challenge in explaining observations, or the fact that these amplitudes are very low on large scales, continues to remain. And so there may be, for instance, surface and deep convection regimes. So there's things that have this on the horizontal axis is radius, and this is very close to the surface layers, and these are deeper layers. We sort of maybe see a transition from surface to deep, which represents maybe different physics deeper inside the sun. As I said, there's a lot of really interesting fluid mechanics that goes into this, but I don't want to describe that in any great detail.
How does one infer
Yes.
the observed details about the velocity below the surface?
That's seismology. So this was what I was saying. These coupling coefficients, so we measure the coupling coefficients at the surface. You followed that? Yeah, so those coupling coefficients here can be linked to the entirety of the properties inside the sun. So think of it very simply as the following. Yes, yes. So you have to be your predictions have to be very close to the, like you can't start from, so the sun is highly stratified. So I can't say that the fluid in the sun is like the air in this room. That won't work because it's just too far. We have to be in the realm of perturbation theory. So for linear perturbation theory, so that you have to be already quite close. But you choose a model that's relatively as a good fit for, for understanding the sun. And we know it's a good fit because we can predict broadly what the frequencies, the oscillation frequencies are in the sun. We do that with great precision. We know we can predict what the frequencies are from our model. So we're in the realm of perturbation theory. And then, okay, so let me just give you a sort of a broad understanding of how this works. Rotation, for instance, the entire sun is rotating in one direction. So waves that propagate in the direction of rotation are sped up, so their travel time decreases. And waves that are propagating in the opposite direction are slowed down, so their travel time increases. So there's a symmetry breaking there. And so we use sort of the difference between these two, this antisymmetric shift, to measure rotation. And so that's sort of broadly how, and you can do it as a function of depth, because you can use different waves that go deeper. You can combine them in complicated ways to find, what's the flow at any depth. And so this is broadly falls under what is known as inverse theory, basically. It's an inverse problem. Yes, yes, yes.
The question is, where lies the problem? Is it the extrapolation from the surface to interior to this perturbation theory, whether that is where the assumption is going wrong or the numerical part is wrong?
So the way we check it, that's why I said there are different benchmarks. So some of the benchmarks are, for instance, can I measure differential? So there are some standard candles, if you will, in the sun that we know exist. So first I take my method and I say, can I match all these standard candles? And then once I do that, then I think, okay, my method works now. It's at least able to match all these standard candles. Now let me push it into a regime where such as this, something much more complicated, non-axisymmetric, time-varying flows. And in that scenario, it seems to be, so unless something has specifically gone wrong when I do the non-axisymmetric case, the overwhelming evidence appears to suggest the numerical simulation is what is wrong. But it's a good question, though. I mean, it's a standard, we keep getting asked this. It's seismology. It's a difficult inverse problem, so referees always ask, it's probably some issue with your, it's the same thing with the solar neutrino problem. The first people to get blamed are the seismologists. And then, whatever, you try all these things, and then you say, fine, I can't discover any flaws in my technique. And then someone comes along and revises the neutrino physics. So anyway, so that's we can also measure the shape of these convective flows using these quantities known as S minus T, which is S is a harmonic degree and T is azimuthal order. So you can say, are these zonal modes of convection? Are these sectoral modes? Different types of shapes, basically, different types of spherical harmonics are excited differently in the sun. So we can measure these modes. Some of those match theoretical predictions. I don't want to get into it. But that's, I sort of want to wrap up here. I think that's about all I have to say here. So the idea, sort of the summary that I want to summarize this work the following, which is to say that there are two ways that our group at least is studying the sun. So the first way is ground up. You take Newton's laws and you proceed and you build a more complicated theory, and then you, like for instance seismology, and then by degrees you match and benchmark your method, and then you can say something new about the sun. The other way to do it is this empirical way where you directly observe the surface layers, which is the first part of the talk that I gave, and use machine learning, for instance, where there's no prior, there's no injection of any physics. It's just a model. You can replace that model by something else. There's no real prejudice there, and from that you derive laws. You derive laws of physics, or you derive these interesting correlations. So both of these are giving us startling new insights about how the sun is operating. Like, so for instance, how convection is working, how flaring processes, how magnetic field emergence is happening, and insights fundamentally into the solar dynamo. So on that note, I'd like to stop. Thank you. Yeah, yeah. Yeah.
Apparently, there's one method, the cosmic ray muons. Apparently, give you a precursor effect which comes before the actual happening of the solar flares. Sunil Gupta in your institute, TIFR, he is doing experiment on that. And apparently he is being supported internationally now to see whether that can be used as a real warning. I don't know, maybe a half an hour window is there when you can shut off all the power grids and things like that.
Interesting. I didn't know this.
Yeah, you please talk to Sunil Gupta,
yeah,
the
okay.
cosmic ray physicist who is working in OT.
Yeah, I know him. I know
You
him.
know him,
but,
right?
Yeah,
Yeah.
I know him. Yeah.
Any further question? Oh,
Very good talk, Shravan. I have just one question about the machine learning aspect application on that. So you are using these different physical parameters in order to find a model. Now, when typically in the machine learning world, you really don't have any physical meaning to any of the axis or the parameter, right? How do you actually expect to find a physical model as a correlation using the machine to find a physical model, to find some correlation along with in this parameter axis?
So these parameters have meaning, the 24 parameters that so these are not the biases and the weights of the network, sorry. So when I say parameters, I don't mean hyperparameters, I don't mean any of those things. When I say parameters, I mean from each of those cutouts, you know, those cutouts you get average magnetic field, average flux, something. So you have all of these spatial averages, let's say 25 parameters, those are the inputs. The outputs are a yes or no question. Is this going to flare or will it not? So we are connecting this binary question to these 25 parameters, basically. And then
So you are evaluating all these parameters independently and ultimately accessing?
not independently. It's a joint. Yeah, it's a joint thing. And then what you can do is you can say, let me get out all the true positives, let me get out the false positives, and study how the machine is reacting to those parameters for those cases. And so just by sort of separating out the successful cases with the unsuccessful ones, you can see how the machine is correctly predicting what the parameters are doing and why is the machine able to do this, and how the machines are, for instance, saying, so something that doesn't flare, if the machine is correctly identifying it as non-flaring, then you see, well, what are the parameters doing for the non-flaring? You know, are these, so you can look at these two things. But we can also do more and more, so the next thing that we're doing, which I didn't describe, is we're doing CNNs to do like this flux emergence. So when does magnetic flux appear at the surface? And that's a very tough question, but you can simplify it saying, can you tell me in the next month how much flux is going to, I mean, there are different classes of questions that you can ask, right? And so then that requires spatiotemporal image, you supply spatiotemporal images. So it's a much more complicated problem. And for that, I think what we're thinking of doing is to try to mask features. So you have to have some a priori expectation, and then the model learns. Clearly the network, by the way, even in that case, a very complicated case, is predicting it with some astounding precision that has not been known before. So we don't even know why it's predicting it so well. So we want to mask features. We want to try to remove some. So these are the experiments that you can do. In a way, sorry, so philosophically, you think about it, people do these giant numerical calculations for various phenomena, right? I'm always suspicious of these highly nonlinear calculations because any number of things can go on with the numerical method in the process of, in this process. Like, there are all these diffusion, dissipation, and dispersion characteristics of the numerical technique. And so sometimes that becomes in itself a giant black box, the numerical calculation. So I'd rather build a black box that is constructed of data and then try to understand, make sense of it, using a variety of tests and tricks and doing this, than to do this. So that's my philosophy. And you can construct, so I'm a bit vague now, so being a bit vague, but you can think, once you start doing it, you can think of different tests that you can apply to this machine. I mean, it takes a little time, sometimes it's very dependent on which class of problems you're solving. Of course, in machine learning in itself, there's an entirety of the discipline that's related to machine interpretation, machine perception, what the machine is doing. But this is a foundational problem, right? So those guys are doing highly mathematical tests of this, which is not something that I'm particularly interested in. What I'm interested in is how can I do something empirically? How can I get some, clearly the machine is doing something. It's learned something, and trying to get it out is.
So this is regarding the differential rotation on the sun.
Yes.
So when you are modeling it using the helium solar seismology, do you put in some parameters concerning the viscous dissipation because of this differential rotation?
We don't do, so this is entirely observational, so we're imaging. So, I mean, it's really no different than someone doing an MRI on you. So there are no real parameters that are put in. Parameters are put in an inverse theory sense, not in the sense of dissipation, or there's no physical, so, okay, so let me take a bit. So dissipation and so on typically come when you do numerical calculations and you're trying to reproduce differential rotation. So the first step, of course, is observationally to understand what's going on inside the sun without any prejudice. But actually, the problem is in inverse theory because it's an ill-posed problem. So you're only observing the bounding surface of these modes, and then you're trying to reconstruct what's happening inside. So you're clearly already starting with a sort of information deficit, and so you have to build this model. So there is some prejudice that goes into it. So there's some regularization, Tikhonov regular. I don't know if you're familiar with this, but there's all these regularization terms. It's more an art than a science. That's what people say. Basically, it is more an art than a science. So there's some shenanigans that go into doing this, but these are not connected to viscosities. They're not connected to this type of thing. It's more an inverse theory challenge. How do I accurately try to do this, without prejudicing the?
Very nice question. So this curl, so this Chandrasekhar kind of states are just the eigenstates of the curl operator, right?
Eigenstate? No. That's one term of it.
Okay.
So I think I know what you mean. Yeah. So this. So this term,
this W is the one.
That's right. Those are the curl,
yeah. And another
null
question.
space of the curl operator. Yeah. Or no. This is the eigenstates of the curl operator. This is the null space of the curl operator.
Okay.
And this is the eigenstates of the.
So since it's a rotating fluid, it's better to work in these eigenstates, eigenbases than to have some other spherical coordinate bases.
It's just yeah. I mean, it's a very powerful basis because the first two terms these are the only terms that are involved in thermal transport. Mm-hmm. So you see this radial term ER. That's the only term here that has ER. So because it has an ER, that means there's a flow that's going radially outwards or inwards or whatever. So that's the term that's actually carrying the heat. So these two terms are known as a poloidal term. These are the terms that are supporting thermal transport, and these are some lateral fluid motions. So the Braycom also has greater physical meaning. I mean, of course, the first thing is their eigenfunctions, as you say, as the curl operator. This is the null space, and this is the eigenfunction. So together they give you some very interesting complementary and orthogonal information. As far as I know, I mean, I'm happy to use other ways to do this decomposition, but there is no better decomposition on the sphere. This is probably the best. It encodes the two-sphere, the periodicity, all of the eigenfunctions. Very nice. Each of these terms is a sigma as a superscript. Sigma is a temporal frequency. So we work entirely in the spatial frequency domain. Spatial wave number frequency domain. So we're able to basically compute these coupling coefficients as a function of frequency as well. I was a bit brief. I didn't know, so a lot of times when I give to astrophysicists, it's a high level of detail. So typically it's a very seismologists are very mathematical. So I don't know if astrophysicists are equally interested in this type of thing, which is why I felt a bit embarrassed and I didn't want to get into the details.
And may I ask one?
Yeah, please.
Naively, is there any region in the solar fluid where there is a chiral imbalance, like more of chiral particles, or is always like?
I don't know. There's some speculation on something happening in the core, but that's the only place where there might be. What is a chiral imbalance?
So it has more left-handed particles than right-handed ones.
There's no way that we would be able to measure this.
Even helicity particles, like different helicity.
You mean magnetic helicity? Or do you mean
even particle helicities, like?
Not that I know of. We would.